everyone, my name is Nur Shafiatira and today I'm going to present my assignment on Bernoulli's principle. So as stated here, Bernoulli's principle explains that as the velocity of a fluid increases, the static pressure of the fluid decreases. In other words, higher fluid speed leads to lower pressure. Alright, so to demonstrate this concept, I have performed a set of fluid dynamics calculations using Microsoft Excel where I analyzed the changes in area, velocity and pressure. From those calculations, I generated two main graphs to clearly visualize these relationships. So let's take a look how it's done. Moving on to question B, let's analyze graph 1 which plots velocity against area. As we can clearly see from the downward trend line, when the cross-sectional area of the pipe increases from 3 meters square to 7 meters square, the fluid velocity decreases from 2 meters per second down to 0.857 meters per second. This perfectly satisfies the continuity equation where area and velocity are inversely proportional, meaning A1V1 equals to A2V2. Next, let's look at graph 2 which presents pressure versus velocity. Based on our plotted data, as the fluid velocity decreases along the pipe, the fluid pressure simultaneously increases, rising from 74 kPa up to 75.63 kPa. This relationship directly validates Bernoulli's principle, proving that a reduction in fluid velocity results in a corresponding increase in pressure. Now let's look at question C where we compare ideal flow with real fluid flow. Bernoulli's equation assumes an ideal flow, meaning the fluid has zero viscosity, mu equals to 0, and experiences zero energy loss. Okay, let's take a look at those diagrams. Alright, however, in real life systems, fluids have viscosity, mu not equals to 0, which causes friction against the pipe walls. So this resistance leads to energy losses, categorized as major loss due to friction along the pipe length and minor loss caused by turbulence from pipe bends and baths. So in comparison, because of these inevitable energy losses, the actual fluid pressure at point 2, P2, in a real system will be lower than our calculated ideal theoretical value of 75.63 kPa. And we are about to reach the end. So finally, for question D, a real-life application of Bernoulli's principle is the aircraft wing or aerofoil. As shown in the diagram, air travels faster over the top of the wing, creating a low pressure zone. So meanwhile, air travels slower underneath the bottom of the wing, which create a high pressure zone. As a result, this pressure difference generates an upward net force called lift, which allows the aircraft to fly. So in conclusion, my project proves that fluid area, velocity and pressure are fully interconnected. And I also showed that real-world friction causes energy losses, making actual pressure lower than ideal theory. Ultimately, these principles are critical for engineering, from piping systems to generating aircraft lift. And that's all from me. Thank you.